Hi, my name is Dr. Mantesh. In this tutorial, we would like to go for the next experiment of this series, that is 32-bit ALU. You can start with ISC as a new project. Give me a second. So you can start with the new project. Go to file, new project, and then type ALU 32-bit, and you can write description. This is 32-bit ALU, and you can give what are the inputs, specifications. In general, we call them as specifications. How many control inputs it should have. Suppose if it is 3 bits, 3-bit control input, we can have say 8 possible combinations, or that means 8 operations we can have. So looking into the syllabus, it is mentioning 4 arithmetic and 4 logical operations. Just as a tutorial, would like to take it as an example. We'll take 3 control, so that 3 control input, that means we can have 4 plus 4, 8 operations. So 4 logical operations, 4 arithmetic operations you can take. You can keep the things as it is. However, as I already told, whatever I have in my lab, I am trying to select. Even you can verify these things on the kit as well. However, you may not be having 32-bit operands, but there is something called I forgot that. Give me a minute. There is something called chip scope for FPGA debugging. Even it supports the smallest device like Spartan 3. In that chip scope, you can give 32-bit inputs, or simplest way to give inputs, even you can mention the inputs A and B in your code itself, VHDL code itself. But you make sure you keep in mind that those 32-bit inputs will take 32-bit locations, or in other words 32-bit flip-flops. Okay, just you can have something called a chip scope. If possible, we'll try to have the tutorial for chip scope maybe in near future. So we'll start with new source, Verilog module, ALU 32-bit. Give meaningful names, ensure that it is added to your project, or else you have to manually add it to your project. Give A, B, just see the code, and if you give it here, half of the code will be pre-written, that is at least module, ports and all pre-written. So just I'm just opening which are all the code available with me. So ALU 32-bit, I have code here. So which has 1, 2, 3, 4, 5, around 5 functionalities. You can have 4 plus 4 because it has got 2 down to 0. That means 3 inputs, 2 power 3, 8 operations. Okay. So I take here, you have to mention, or else you have to write it manually. So what I do now, I just selected everything and deleted, and then right click, paste the module. You can always mention time scale as the first line here. At this moment, since it is combinational logic, the time scale does not make much difference, but anywhere the boot multiplier has a clock, so in that case it is better. Flip-flops have clock. In that case, you better mention the time scale, 1 nano by 1 pico or something like that, which is a good practice. Even in test bench, you better mention time scale, which has got its own good advantages. So those things can be observed very clearly while doing simulations. So we'll start with simulation. You can give without test bench as we did it previously, or we can take test bench and you give some test cases and then you can do it. So now we are directly going the same thing what we did previously without test bench. That can also be done for this module as well, or we can test it if you would like to spend few minutes. Simply go to simulation. I'm trying to do as fast as possible. Okay, there is an error. What it is mentioning? Which line? Cannot find your design in it. Okay, I have to click here. BL chat syntax. Okay, fine. Okay, I think I got now. This is iSim. Without test bench, we are trying to do simulation. So what I am trying to do, A, B are inputs. So I cannot give 32-bit ones and zeros. So what I do, this is essential now. Unsigned decimal, make it unsigned decimal, so that you can give numbers easily. 32 by 4, it is going to be around 8 digit. 8 digit I can make it. Okay, not a big deal. Radix unsigned decimal. So what I am trying to do, I'll give 08 for you can make force constant. 08 maybe some number, good number. So this is 0000009. Force constant, you can take some big number, 25 or something. It's also acceptable. Then functionality 00, force constant. 00 means what is there, we have to check. 000, A and B. 25 and here I mentioned 9. So you just have to do AND operation and simply hit. So you got 9. Okay, 25 means the 2 will go anyway. 5 will have 101. So this 1 will come here. So the answer is correct, 9. Fine. Functionality, we'll just have to check one more time. What if 000? It is A and B. Next 001. What if 001? Force constant. That is 001. Apply. Okay. Run it. So what if 001? It is OR operation. OR operation means 25, correct. So this is how you have to verify. You just go on changing the functionality 1, 2, 3, something like that. So without even test bench, since it is the simple design, it is possible. For complicated design for a given specification, this method what I am telling now is not a good idea. Next 25 plus 9, it is 34. For 2 it is addition. So like that you go on giving the values for F. Even you include more and more functionalities. I have included only 1, 2, 3, 4, 5. You can have many more. You can have XOR, XNOR, negation. Okay. Suppose if I try to do with same thing with test bench, you just go Verilog module, 32-bit. Okay, select Verilog module, ALU, 32-bit. You cannot write 32-bit ALU because there are literals. All the literals, names and keywords all should start with alphabet, should not start with number, should not end with underscore. There are many rules are there. Two consecutive underscores not allowed. Anything other than underscore, any special characters other than underscore not allowed. So there are some rules, you just have to read those. In the theory probably you might have studied. Sorry, I think I made a mistake there. I have to take a Verilog module, ALU test. Next, Control A, delete. Then I have ALU test bench, which is very simple. I'm just pasting it. These codes I'll be sharing with you through some links. You can directly download these codes. So here I have given 5 and 4 the numbers. Just simply save. Go to simulation. Already you can see that as soon as I save, this 32-bit ALU is added in the as a instance in the test bench. Simply hit simulate behavioral model. So now it's saying why it is why. Let me check. Oh, here I am getting output, but I have to zoom it. So this 1 microsecond can be reduced to avoid this confusion. So simply what I do, I'll just restart. Instead of this 1 microsecond, for this experiment you can make 250 nanosecond. You just check what is there in the test bench. How many? Okay, 10, 10, 10, 50. So around 100 nanosecond, everything will over. So you are getting other values. So you keep it as 100 nanosecond. Nano. Okay, and just run. But still, you could see that there are some excess, but it's okay. Now I already told you convert this radix because reading 32-bit number is difficult. Change the radix to unsigned decimal for simplicity. So this function you can keep it as it is. Take this f down so that it will be easy for you. So a is this, b is this, a is 5, b is 4 for all combinations. In between also you can change. If 0, 0, 0, 5 or 4 it is 4. Sorry, 5 and 4 it is 4. For 0, 0, 1, 5 or 4 it is 5. 5 plus 4 for 2 it is 9. 5 minus 4 it is 1. So on. So 5 into 4 it is 20. So this is how things work. You can add many more functions. What is 101? What is 110? You can add another 2 and 3. Total 3 functionalities we can add additionally. Next, we are supposed to do synthesis for this. Okay, this is all about simulation. Synthesis, go to implementation, remove this test bench. It may disturb the synthesis because test bench is for functional verification only, and testing or verifying our functionality of the design. That is not actually the code. Okay. Next, I have some warnings because all combinations are not covered. You could able to see that 101, 110, all those things are not covered. So those warnings, one or more mixing signals, you can find all those things. ALU 32-bit, you could able to see only F is variable. Along with F, if A and B are changing, immediately it will not respond. So you can add A comma B as well to avoid these warnings in the sensitivity list. So any change in A and B along with F will change output. So this is good. Okay. Anything 32-bit partially used. Okay. This is multiplayer. There is no direct library instance available. So what it is saying is we have 64 I think 64-bit or 32 by 32-bit multiplication. We are using it partially, what it is saying. We are not completely using it. If at all, if you want to see how to use multiplier, you can go to new source. You can have IP core. There you can have multiplier. If you want, I can show you how to get multiplier or how the FPGA will get multiplier because there is no ALU inside. You yourself building an ALU now on FPGA, so there is no multiplier. Everything must be done with respect to, so it may take some time. Meanwhile, we'll finish our synthesis. Okay, but before I cannot do synthesis now. So we'll read the synthesis report by clicking here. Where is the design summary? Okay, it is not allowing me to do. So let me show you where are multiplier. There are many things using these. You can do your mini or micro projects. You can search for multiplier simply. There is basic accumulator is there, and multiplier is also there. Can you see? There is complex multiplier and simple multiplier. It is going to use this multiplier. Okay, as soon as you type multiplier, because I have you may not get this because I have full. You may get, but you may not get as well because I have license for these things. Okay. Simulation wise it is okay, no problem. You continue with the simulation. I am trying to synthesize it. I'll go to design summary and read the synthesis report for critical path and maximum delay. The critical path mentioned as, here is the critical path or data path. It starts with 813 and ends at Y31. This is the critical path or longest path, and the delay which is produced is 24.464 nanosecond. And device utilization or number of cells used, here it is mentioned clearly, 86. You take this in the form of table directly. The table can be copied from this. So this is a table. You can directly copy this table. Okay, copy, and you can put it in the Word file or somewhere. Then you can copy it to your directly. So this is all about ALU. You can also find, as I already told, power analysis for this, but still you will be seeing this is combinational circuit. There is no dynamic power. Dynamic power requires CV square F. F is not there. At what frequency we are trying to operate ALU, we still have not yet figured out with this design. So in that case, you may not be able to see the dynamic power still. However, we have the static power, which is around 27 milliwatt, which is almost same for all design. Suppose if it increases, this may increase. Also, this is going to come in picture. Now it is showing 0 because it is less than 1 milliwatt. Anyhow, that's all for this tutorial. See you in the next tutorial. See you.